Pete, and GSTEC committee for organizing this. I'm going to enjoy telling you about some of this research that we are doing here at CSU, but mostly about this field that's become known as brain-computer interfaces. So I just want to first introduce the general idea and some of the terms to you. And as Pete showed you, talking about the past and the technology is very helpful in understanding the future. So I'm going to spend a little bit of time on the past and the present, and then give you some of my speculations about where this field is going. So first of all, why does anybody want to consider directly connecting a computer to your brain? Sounds like a strange endeavor. First of all, I want to say that a lot of the work in the field, including ours, is just using electrodes that are placed on your hair, on your scalp. There's nothing invasive about it, but there's a lot of work that does go directly to the brain. We'll talk about a little bit about that. But some of the questions or answers to why are these 5 listed here. The first one is the most common, I'd say. A person who's become paralyzed through an injury or through a neurodegenerative disease perhaps can have some of their actions or behaviors that were available before become available again. If we can detect something about some intention via brain waves from the brain and use that to control a wheelchair or a prosthetic arm or make choices on a computer screen, then that person has some restored function. And of course, restoring function can be done by directly stimulating muscles in the limb through some input from the brain. We could also enhance a person's behavior or even living or functioning in a difficult task. There are currently ways of detecting when a person's attention lapses, or you're driving a big rig truck or controlling a nuclear power plant. It'd be nice to have some kind of signal that indicates that you're losing attention or you're starting to get drowsy. Also, perhaps supplement a person's abilities. This is a bit more into the future, where if you have some way of controlling a third arm in some task by changing what you do in your head while you're also moving your 2 real arms, that would be quite a feat. And in general, to be able to improve your functioning in normal life, especially for people who have suffered strokes, some of these user interfaces or brain-computer interfaces may provide ways of restoring that function by directly rewarding your behavior and how you do things mentally, and be able to recover function much faster. So there's some answers to the question why. So what are brain waves? There's a lot of text here on this, but you know that our brain is composed of lots of individual cells that interact electrically and chemically, and the activity of a single neuron cannot be measured on the scalp. It can be measured by an electrode placed inside your brain, of course, or any nervous tissue. But it's a complicated network of cells. When a large number of neurons, in order of hundreds of thousands, in a small region of the outer part of your brain fire together, or the activity is synchronized somehow, then that current is enough to be detected on the scalp. It has to add together and get through all the cerebral spinal fluid and skull and skin to get there. So it's quite a long ways for that electricity to get to be measured. And electroencephalography, or EEG, is a measurement of these weak potentials, and they are weak, 10 to 50 microvolts, which is about what you get if you put up an antenna and get radio waves coming in. So it's a tricky business measuring these signals. You can measure EEG using electrodes placed at multiple scalp locations in a cap like this red colored cap this person is wearing. This is exactly the kind of caps we're using in our research. There are standard positions given by those colored circles where these electrodes are placed, so you have some consistency from one subject to the next. The graph in the upper right shows the typical graph of 1 second of EEG. You can see how quickly it changes. It looks like noise, and a lot of that probably is electrical noise from the environment. But there's something in that signal that relates to what the person is doing mentally. And the bottom right shows something about how broadly, or how little precision spatially there is on the EEG. When the area becomes red, that's a positive voltage, and you can see it's a fairly large area of your scalp that looks like it's firing together, but that's probably due to the fact that this current gets swamped spatially as it goes through the skull and skin, so it's not a very precise spatial measurement. So let me talk a little bit about the past in this field. In 1875, electrical signals were first measured on exposed animal brains. That's quite a while ago. It wasn't until 1924 that Hans Berger used an adapted radio amplifier to actually record these signals. And he coined the term electroencephalogram. And those are little traces of some of his original signals. And he actually identified some of the rhythms, oscillations that are known in the brain that have not been rediscovered. They've been known since 1924. In '64, Gray Walter placed electrodes directly on the motor areas of the patient's brain. The motor areas, that purple region shown on the right, and some in the red region also. So that was known, and so he was able to record directly from there, and the electrical activity recorded predicted the moment when the patient was going to press a button. So this was really the kind of the first brain-computer interface directly on the brain. And in '69, an electrode was placed in a monkey's brain, and the monkey, by observing the electric meter showing how much activity there was in that neuron, was able to control that meter in order to get some food. In '73, Jacques Vidal recorded scalp EEG, showing you wouldn't have to go into the brain, from 5 electrodes over visual cortex, and detected which of 4 areas on the computer screen the subject was looking at. So this is over, what, 45 years ago. We aren't much beyond that now, but as I hope you'll see by the end of this talk, it's accelerating very quickly, and we may see some great advances soon. But I'll show you some very curious things here at the end. So the present, I want to talk mostly about present BCI, or brain-computer interface applications, based on things we know about EEG. These 3 things: expected stimulus causes a change in EEG, or flickering images causes flickering in your EEG signals. And imagined movements will cause certain changes that we know about also. And those have been used to design brain-computer interfaces like I will show you here. So in this case, is an example of a stimulus that's rare but expected. So if you're seeing letters flashed on the screen, like D, E, F, one at a time, right over each other in the center of the screen, and you're looking for an A, or you want to type an A, whenever that A appears, we should see a graph of your EEG signals on the right side here that are colored, you see that, red or cyan. So at about 300 milliseconds, which is the x-axis here, after the stimulus, which is the vertical dotted line, there should be a positive wave, which is why it's called P300. But if it's any other letter, you'll get a lower wave. So that is meant to, or we think that represents your cognitive realization that that letter appeared that you were looking for, a rare but expected stimulus. You can do this with auditory inputs too. So if we can detect that reliably, we can detect which letter a person is looking at by arranging the letters in a grid like this and flashing rows or columns in random order. And if you want to type the P, whenever that row or column flashes, we get that P300 wave. This was done back in 1988, still quite a while ago. It still takes a lot of trials to average the signals over to find that P300 wave. But here is a little video showing what it might look like. It flashes at about this rate, and they're trying to type the letter S, the person using this. And eventually, after 50 repetitions, you'll see a little S appear in the upper left part of the screen. I know this takes a while. Maybe we won't even wait for it. Let's see. Yeah. Okay. Wait for it. This is typical of these brain-computer interface systems that we have now. It takes a long time to get any response because those EEG signals are so noisy. And this is using a single electrode. There, they got the S to start the word shoes. So as I said, you can also detect which pattern a person is looking at. So if you imagine that upper left picture filling the computer screen, so you have 4 grids, checkerboards, flashing at different rates. If you look at one of those, I'll go back to this again, we can detect which one you're looking at by seeing what frequency appears in your EEG as recorded from the back of your head, which is where the input from your eyes go, back here to visual cortex. And that can be done fairly reliably. In the bottom right, you see something where we're determining which checkerboard you're looking at by the staircase, the blue dots, and we're fairly accurate. They're moving from one checkerboard to the next in about every second. So that's been used in game situations like this, where on the right side you see a little race car moving around a track with the checkerboards around them. So if you look at one of the checkerboards, you can steer the car in that direction. And that works pretty well. It can get fairly annoying if those checkerboards are fairly big and flashing at a high rate. It might be more tiring than moving a joystick even. But if you can't move a joystick, this may be an alternative. a number of people, not everybody, but a lot of people through biofeedback training can learn to control the energy in 2 different frequencies in their EEG over motor cortex areas. And this is an example of somebody controlling the small square moving around towards the large square, which is the target, just by thinking. And they might start off with some mental task like run fast and walk slow to move it up or down. But with a lot of practice, a lot of subjects report they just imagine the cursor moving to a certain position. So it becomes very second nature, just like you learning to play tennis, where you have to focus really well on the first few days of training, but eventually it becomes second nature. You can also use that cursor movement to spell, like this. If you just have one dimension of control, we have a cursor moving at a constant speed from left to right, but you can move the vertical placement up so that you can select a certain part of the alphabet. This looks like it's typing faster than that grid of letters than it usually is. Okay, you get the letter S. And finally, this last example of using some of the known responses from EEG. This was a project that was described by Jose Milan, who visited CSU several years ago. This is one of his students who is controlling a wheelchair. This person is not paralyzed, but he's illustrating what can be done. He is imagining left foot moving to turn left, right hand moving to turn right, and imagine words in his mind to start with a certain letter to go forward. This looks like it's working very well, but in order to get this to work, they had to build a lot of intelligence into the wheelchair. This wheelchair cannot run into anything. It has distance sensors around the base of it and laser rangefinders, so it will not run into anything. Only when there's a choice to make will it consult this little brain-computer interface. So there are a lot of difficulties of measuring EEG, as I said. Electrical noise in the environment from all kinds of sources, including assistive devices. We have recorded EEG in people's homes who have a hospital bed and found out if we unplug the bed, we reduce the 60 hertz noise tremendously. So there's lots of experience that goes into that. And the electrical signals from the body. When you blink your eyes, you get a large change in the EEG. These are all referred to artifacts. We want to remove them because we want to be sensitive to the brain itself, not to other artifacts that might interfere with our detection of what the person intends. So here's an example of some EEG we've recorded from 60 electrodes, and the bottom left shows the eye blink, which is a sensor next to the eye. And with some help from Michael Kirby in the math department, we've come up with some ways of separating the various components of this. And on the right side, we see all the components. On the upper right, we see that the eye blinks have been isolated to one component. They're not in the other, so we can mathematically subtract that from the data and go from the left original data to get the right side data without the eye blinks. Limits of current methods. Takes a lot of time to put on and to train people. Reliability isn't good. We have to average over lots of examples, and they're expensive systems, $20,000 to $50,000. So, as part of the present section of this presentation, I'll tell you about some of the work we're doing. Our approach is to find inexpensive, off-the-shelf EEG equipment. We're not creating any new hardware, and we find that we don't have to. The expensive parts of these systems often are the software, so we are writing our own software. We are a computer science department, and making it free to people who want to experiment with these devices. We're using multiple electrodes and finding patterns across multiple electrodes to get better results. Better machine learning procedures to find the patterns. And a limitation of the current approaches are that most labs have not actually gone out into the world to see how well these devices work in people's homes. So the past couple of years, with the help of Dr. Patricia Davies there and Dr. William Gavin at CSU and Michael Kirby from that department, we've been taking our equipment out into people's homes in Fort Collins and the surrounding community who have suffered from spinal cord injuries or multiple sclerosis or other motor impairments, and seeing how well we can record the signals and how well we can classify them. And this is just an example of, this shows Patty Davies recording from a person with a spinal cord injury. We've compared this equipment made by a company in Colorado, Neuropulse Systems, which only costs about $7,000 for the whole thing. And we are now experimenting with this wireless system from Austria. It isn't that much more expensive, but it communicates through Bluetooth, through a laptop, so we have to have the computer close to the person to the experience. And we're writing our own software, so we can classify which mental task you are doing, and I'll talk about that in a second. We can select different parts of the alphabet, for example, and type with that. Mental tasks we've looked at are imagine right hand clenching, imagine left foot moving up and down, count silently backwards from 100, and imagine this computer screen tumbling in 3 dimensions. These are all tasks that we think will produce different patterns in your brain waves, But this is the problem. We don't know how the brain does these tasks. This is wide open. We just have to do some of these machine learning methods to find statistically significant differences. Here's one quick result. If a person did 4 mental tasks in a row, this little square wave shows the actual task, 1, 2, 3, or 4, and the dark circles are where our system is identifying which tasks they are performing. And it's working very well, except between roughly 15 and 20 seconds, you see there are no classifications, because our system found that we are not able to reliably detect which one the person is doing. And we don't want to make any predictions in that case. So, I have a few minutes left, let's talk about the future. It's going to get really exciting if it isn't already. There's been a rapid increase in publications. This is a little graph. You see the last graph is from 2008 to 2010, and it's continuing to skyrocket. It's just phenomenal. You've been seeing it on popular press or in airplane magazines already. Just a little indication of what's coming. There are some new methods, particularly one done by Elliot Forney, who's a graduate student here, who was modeling EEG. Here's an example of a top row is a simple model, then a more complex model, and even a more complex model on the bottom. The middle one kind of locks into a certain frequency to model your EEG. The bottom one actually makes realistic looking EEG, and if you look at some of you engineers will know the frequency response here, the bottom right, to the right of the vertical black line, it looks a lot like real EEG. It's very complicated. I just told myself I wasn't going to say this, but it's like this, the bottom model is finally waking up. It's actually generating some interesting EEG. New sensing technologies are coming out. This near-infrared technology looks like quite a wild science fiction cat, but this is done by Honda, and they controlled Asimo, the Honda robot, with this. I'll show you a video later if you'd like to see it. And then here's some more invasive methods. People with epilepsy often have their heads opened up to implant electrodes to better control their seizures. But at the same time, we can use input to do better brain-computer interfaces. And I think this will work for us if I think I'll show you this later too. You can reconstruct speech from a person's EEG. At least I should be able to show you this video. fMRI, it's a huge, expensive system, and here's one in the upper right. It's a whole room full of equipment, of course. Perhaps someday that will be reduced down to something more practical. But very recently, there's a group at Berkeley was able to reconstruct images a person was seeing just from the fMRI signals. We'll see if this is going to work for me. Here's a video. On the left is the presented video to this person, and on the right is what's reconstructed from the brain activity. It looks muddled, but it's amazingly close. Think about it that way. So that's kind of it. The beginnings of what you might call mind reading, really detecting what images or speech or words a person is thinking. So, let's see. Get there. I'm trying to restarting my slideshow, of course. There we go. There are new EEG devices that you see being sold by video game companies. We're not sure what they would be used for and whether they're actually detecting EEG. There's lots of snake oil out there, so you have to be a bit speculative. But I did want to show you quickly one of the new applications that really surprised me. This is from Japan. I had not dreamed up this application. But these little rabbit ears are sensitive to how much concentration you have or how excited you are. Oh, that's a good donut. When they're relaxed, ears go down. The consumer market is anything you can dream, right? And of course, new idea of social networking. So these are just starting to be sold this year. Who would have imagined that? I certainly didn't. Future BCI applications. This is about my last slide. More speculation. Rehabilitation, of course, is an obvious use, and that's being investigated now. Faster mental typing. Maybe you want to silently type while your hands are doing something else, to type words, letters, or even words if you can get the speech understood directly, like the one slide I had. Surf the net, select choices in a browser can be done fairly straightforwardly now. Polygraph machines, This is a real invasion of privacy, and there are lots of discussions about the ethics in this field that are very important to consider. Music production, people are now actually producing music directly from brainwaves. Direct input to the brain is a bit farther into the future, but it's being looked at now. In fact, on campus, Matt Malcolm here in the occupational therapy department is using magnetic fields to modify your brain activity. We already have artificial senses in artificial cochlea and retina, and they're beginning to have artificial touch senses. Maybe we could inject memory someday if we can actually understand. This is getting really into the Star Trek realm. But I believe that some simple forms as we may be seeing in the near, maybe decade, 10 or 15 years. Direct user-to-user communication. Can you imagine two people using a device, maybe it won't be cat ears, but some kind of devices where you're actually communicating through the net or even in the same room without talking, without doing anything. Yes, you can do this with sign language across a quiet room, but who knows what the possibilities are. Maybe it'll be even faster than verbal communication. This just kind of blows my mind when I start thinking about the possibilities. So, for more information, you can look at our website that's listed there, and a new book has just come out this year by a lab in New York State by Wolpaw and Wolpaw. Brain-computer interfaces, principles, and practices. That's a great resource to really learn about the latest developments in this field. So with that, I'd like to thank the chance to talk again, and any questions?
We'll take them later.
Okay. Thanks very much.